Thank you for tuning in to the 2020 Mineral Symposium of the Pacific Northwest chapter of Friends of Mineralogy. This is our first virtual symposium due to the current health restrictions because of the ongoing global pandemic. So we're glad that you're able to join us here today. Our final presentation for this year's symposium is a man who will challenge the way that you look at colored minerals as he addresses our 2020 theme, Aesthetic Minerals, Color and Crystallography. I'm very pleased to introduce Dr. George Rossman. George is Professor of Mineralogy in the Division of Geological and Planetary Sciences at California Institute of Technology in Pasadena, California. He got his bachelor's degree in chemistry and mathematics from Wisconsin State University in Eau Claire and his Ph.D. in chemistry at Caltech. His principal research interests deal with the use of spectroscopic probes to study minerals. His work addresses problems relating to the origin of color phenomenon in minerals, phase identification, and the special role of metal ions in minerals. He and his students develop analytical methods for the analysis of hydrous compounds in minerals and examine their role in modifying physical and chemical properties. He is also interested in the long-term effects of minerals from exposure to background levels of natural radiation. George was a recipient of the first Dana Medal from the Mineralogical Society of America in 2001, the Richard P. Feynman Prize for Excellence in Teaching at Caltech in 2004, and the Friedrich Becky Medal of the Austrian Mineralogical Society in 2005. He was also honored by having a new mineral of the Tourmaline group, Rossmanite, named in his honor. He has more than 360 publications in the mineralogical and chemical sciences. And now Dr. George Rossman with his talk, Natural Radiation, A Tale of Two Minerals.
Well, thank you very much. It's my pleasure to be able to be here and to give you this presentation today. I'm making this presentation from the California Institute of Technology in Pasadena, California. I'm currently in the Division of Geological and Planetary Sciences. And I'm in a room where we have a small museum of various mineral crystals, including a lot of the minerals from the California Pegmatites that are behind me. These will be part of the focus of my talk today, trying to understand the origin of color in some of these minerals. My talk today is about natural radiation. It's a tale of two minerals. It's a tale of the Feldspar group minerals, and it's a tale of the Tourmaline group minerals, in particular amazonite and pink elbaite tourmaline. We're going to start with the Feldspars. The Feldspars are a group of minerals. In fact, they are the most common minerals in the Earth's crust. There are three common chemical varieties: potassium feldspars, sodium feldspars, and calcium feldspars. They come in a variety of colors, like you see here, from colorless to iridescent colors to pink, for example. The question I want to ask is, what is the color of an ideal, textbook perfect end-member feldspar? And in particular, the potassium aluminum silicate, orthoclase microcline, the sodium aluminum silicate, elbaite, and the calcium aluminum silicate, anorthite. We can go around the world and we can collect these different minerals, and we find very commonly that we can get them, but we find also from a study of the chemical properties that potassium, sodium, calcium, aluminum, silicate, and the oxide ion itself, none of these can cause color in feldspar. If these were the only components in the feldspars, they would be absolutely colorless. And the samples that we have collected around the world, we can look at them, and we find, in fact, that a lot of potassium feldspars are colorless. Same with the sodium, and we can find colorless calcium feldspars. So this is perfectly consistent with our understanding of their chemistry. And even if we look at some of the less common varieties, or should I say compositions of feldspars, buddingtonite, halophane, and celsian, which are the ammonium, the barium, and the barium-potassium feldspars, we can also find that these can be colorless in nature. But we also can find in nature feldspars that are not colorless. We can certainly find pink feldspars from the Midwest. I grew up in Wisconsin, and I grew up believing that all potassium feldspars were pink because they were, back there at least. And if you collect the beautiful gemmy transparent feldspars from Madagascar, the Sanadines, yes, they have a faint yellow color to them almost inevitably. And of course we have the colorless feldspars, but that's not the real concern today. If we take a look at the Plagioclase feldspars, labradorite, bitonite, antacene, things like that, we find that very commonly they have a distinct yellow tint to them. And that is almost anywhere in the world where you collect them. So we can analyze these, we can do chemical analyses, and we can do studies of the color. And we find that the yellow color, which is so common in both potassium and Plagioclase feldspars, comes from iron in the +3 oxidation state. This iron is replacing some of the aluminum in the tetrahedral framework, and it's an essential component of these feldspars, at least at this small weight percent compositional range. Of course, we all know about feldspars that have beautiful iridescence, like the labradorites from Madagascar. This is a color that comes from layering of compositional different layers, kind of like a butterfly wing, iridescent colors, or a scale on an insect. But that's not the topic of today's discussion. And then we come to the red feldspars, which are so common around the world. The red color in these feldspars is the color of tiny micro to nanoparticles of hematite. When these feldspars grow, they naturally incorporate some iron that's in the aluminum site. And over geologic time, tens of millions, hundreds of millions of years of time, water can percolate through these feldspars, very, very slowly, but it does go through, and it can react with the iron and cause it to precipitate out as hematite. And that is the common color that we see in many of these red feldspars, little teeny particles of hematite. And of course, we can worry about the red feldspars in the Northwest, in particular the Oregon sunstone feldspars. The red color in these feldspars comes from copper in the elemental zero oxidation state. Small clusters of a few atoms of copper give rise to that transparent red color. But if they grow into larger clusters, you can actually see the metallic copper in the feldspars, the schiller. Where I really want to go today, however, is with the Amazonite variety, these beautiful blue feldspars we find from the Colorado area, Pikes Peak area, Lake George area, and also these beautiful blue feldspars, for example, from the Kola Peninsula in Russia, and many other localities around the world. They are potassium feldspar, potassium aluminum silicate, but there's something special about them that gives their beautiful blue color. We can also find green feldspars that are also called Amazonite. These are beautiful examples. The one on the right is from Broken Hill, New South Wales, Australia. These have been known for a long time. And much more recently, beautiful green Amazonite feldspars have come out of Luqian, Vietnam. And again, these are potassium feldspars. The material from Vietnam can sometimes be so beautiful and so transparent that it's actually entered the gem world. And these are examples of some of these beautiful transparent Amazonite feldspars from that Vietnamese locality. So the question I need to ask is, what is the origin of the color? Where does this blue color come from? And certainly the Pikes Peak area of Colorado is one of the more prominent localities that we know about for giving rise to beautiful blue Amazonite. So what do? Well, we take 3 different colors of Amazonite from specimens that we have. We take the greenish material from Broken Hill, New South Wales, Australia. We take the beautiful deep blue color from Lake George, Colorado. And we take an intermediate, somewhat bluish green or greenish blue color from the York Mountains in San Bernardino County, California. And we're going to conduct a number of different tests on these to see if we can learn some insight into what is the origin of the color in these Amazonite feldspars. One of the first things we do is we take these crystals, take off a piece and break off a piece, and we polish it into a little slab, doubly polished, like it's a little window that we can use to examine the quantitative measurement of the optical absorption. We find that there are really three types of amazonite color, and we can see them in the three samples. The Lake George, Colorado, the blue material absorbs sort of at the center of the orange region of the spectrum, with tailing into the green and into the red. And the maximum transmission of light is in the blue portion of the spectrum. It's the area where we get the least absorption of light, and that causes the blue color in the sample. The material from Broken Hill, Australia has a similar looking spectrum, but it's shifted over to the right, more into the red. And here the peak absorption is very far into the deep red, and the maximum transmission now lets a lot of the green wavelengths come through that accounts for the greenish color of these samples. And interestingly, the sample that we got from the San Bernardino County, York Mountains, that is a mixture of these two different types of spectroscopy occurring simultaneously in the sample that gives us an intermediate color. The spectrum itself doesn't really tell us about the origin of the color atomistically, but it gives us some insight into the difference between the green and the blue. We got to look a little bit further now into the structure of feldspars to understand some of these differences. The structure of feldspar is what we call a framework silicate. It's made up of a framework of aluminum and silica tetrahedra. The alumina tetrahedra are blue on my diagram, and the silica tetrahedra are red. We don't show the oxygens. They occur at the intersection of the various tetrahedra. There are two fundamentally different ways that we can get this aluminum and silicon in the feldspars. On the right-hand side, we see an ordered version. For each of these ring of 4 tetrahedra, the aluminum ion, which is the blue color, occurs at the bottom of the ring of 4. Whereas in the disordered variety on the left, the aluminum can change places in the different tetrahedral rings. In the top one, it's at the bottom of the ring of 4. In the center, it's to the right-hand side of the ring of 4. And in the bottom, it's on the left-hand side of the ring of 4. We call this a disordered arrangement of the aluminum and the silicon compared to the one on the right that has a perfect ordering, all the aluminum at that bottom position. We also can envision that this difference can cause a subtle difference in the color of the mineral if other atoms are present in the crystal that are interacting with the tetrahedral framework. The aluminum has a little bit less positive charge than the silicon, so we can envision that if there's an atom closer to the aluminum, it may have a slightly different behavior than an atom closer to the silicon. And this could show up as subtle shifts in the wavelength at which these samples absorb light. The difference is named in the nomenclature. The more disordered feldspar is called sanidine. That forms at high temperatures, typically in volcanoes. The more completely ordered feldspar is called microcline, and that typically is in bodies of rock that have had millions and millions and millions of years to cool slowly, where the atoms of aluminum and silicon physically migrate and rearrange themselves into the more ordered environment. And the intermediate amount of ordering is what we call orthoclase. What we find in our studies is that all of the green feldspars have a disordered arrangement of the aluminum and the silicon ions. And all of the blue feldspars that we have studied have an ordered arrangement of the silicon and the aluminum ions. All of them are still potassium aluminum silicate, but the ordering of the aluminum and the silicon can shift the color from blue when it's ordered to green when it's disordered. This still doesn't explain why they're colored, but it gives us some insight into why we can have this difference between the green and the blue feldspars. The next thing that we have to do is chemical analysis. We have to run complete chemical analyses on these feldspars. We have to see if there are other small concentrations of other elements in the feldspars that could be responsible for the color. And the chemical analysis is going to be one of our biggest clues into the origin of the color of these feldspars. To do that, we use an instrument known as an Electron MicroProbe. This is our instrument at Caltech. Over on the left, we see a column with a big wire on the top, big thick wire. That is the electron gun, where electrons are coming down the column, which is under vacuum, and striking our sample, which is located in the lower compartment. When the electrons strike the sample, they cause the sample to give off X-rays, but every chemical element in the sample will give off a different wavelength of X-rays. And the X-ray detectors that are surrounding the central column detect these X-rays, and they can tell us how many counts from iron, how many counts from aluminum, how many counts from silicon, and how many counts from any other element that might be in the sample. With suitable calibration of the detectors, which is what we do, of course, we can get a very good quantitative, rigorous analysis of the chemical composition of these feldspars. So what do we find? Well, we find, first of all, that all blue feldspars contain lead and all green feldspars contain lead. The arrow is pointing to a blue region in one of the Colorado amazonites, and there is lead, the element lead, chemical symbol Pb, in this blue region. How much lead? Well, we have done rigorous quantitative analyses. In taking my test samples, we find the one from Broken Hill has almost 1.8% lead. The one from Lake George, which is the dark blue sample, has 0.05%, much lower concentrations. And the one from New York Mountains has slightly more at 0.078%. But the color on these is pretty much the same. It seems like it's not just the amount of lead, but something else must be going on too. And on the right-hand side, I show you some analyses from other localities around the world, just to show you that these are typical ranges of the lead content of the feldspars. Remember, all blue feldspars contain lead, and all green amazonite feldspars also contain lead, and these are the typical concentrations. We believe that the lead is going to enter the feldspar in the potassium site. Lead commonly is in the +2 oxidation state, and that would substitute in the potassium site. It would fit and it would go in there as something that we could expect. This means, of course, that when the feldspar grows in nature from the original magma body, there has to be lead available in the natural environment, and the feldspar is going to incorporate this lead when it grows from the material that's feeding the growth of this feldspar. Now, life, unfortunately, isn't quite totally simple. We can find samples of feldspars that contain lead but are not colored, like that white overgrowth on the Pikes Peak sample to which the arrow is pointing. We find these in many localities around the world. We find mixed white and blue feldspars. Inevitably, the blue feldspar contains lead, and the colorless white feldspar also contains lead. This is kind of a puzzle because it somehow casts doubt on whether just lead per se is causing the color in the feldspar. If there's lead in both regions, why aren't both regions blue if lead alone is the cause of the color? So we're going to have to dig deeper into the feldspars and see if we can understand at a more fundamental level what else might be going on. We put all of these feldspars through infrared spectroscopy, and that is a technique that's sensitive to water. And we find that all amazonite feldspars, whether they're blue or whether they're green, contain water molecules literally bound in the structure of the feldspar. No exceptions whatsoever. Furthermore, we find that if we have lead-containing feldspars that are not colored, they do not contain water. This was the thesis work of one of my students many years ago. So now we have amazonite contains lead. The green versus the blue depends upon the structural order of the aluminum and silicon framework. We have to have water as well in the feldspar, as well as lead if we have the blue or the green feldspar. So here's what we think is going on. We think that in normal potassium feldspar, potassium ions enter in their normal structural positions. But if the feldspar is growing where lead is available at some concentration, occasionally a potassium site will be replaced by lead. But lead comes in the +2 oxidation state, and that's more charged than the potassium. So that means the potassium site immediately adjacent to the lead is going to have to be either vacant or contain a neutral molecule, but it cannot contain potassium because that would be too much charge. So this is the way we think both lead and water get into Amazonite, and we'll call this now the Amazonite substitution. Does the lead cause the color? Well, we're going to go to the chemical laboratory now and get bottles of lead chemicals. Lead nitrate, lead phosphate, lead sulfate, lead chloride. And we're going to find that all of these lead-containing chemicals are colorless. Lead +2, it seems, cannot be the cause of the color in the Amazonite, even though we have just demonstrated that all of the Amazonites contain lead. So it has to be more complicated than that. We're going to do another experiment. We're going to investigate the thermal stability of the color in the blue feldspar. Can we heat it up and make the color go away? Does the color stay the same? Does the color get darker? Maybe we'll learn something from a heating experiment. So we take a piece of the feldspar like the one you see here, and we put it in a furnace for a short period of time, and we see what happens. Here is what happens. We can easily remove the color, the blue color of the Amazonite feldspar by heating it at 800 degrees for just 1 minute. So all it takes is 1 minute to completely remove the color. What we know is there are many things called radiation damage centers that behave this way. Sometimes they're called color centers. They're very easily removed by heating the material, so that gives us a possibility that maybe this is a radiation damage center, a color caused by radiation. So we're going to ask another question. Can we take this blue feldspar and heat it and remove the color and then re-irradiate it in the lab, take the colorless material and irradiate it, and can we turn it back into a blue crystal? We did this, and here's what we found. Yes, we can bring the color back if we irradiate it with gamma rays. This is exactly what we would expect for a radiation damage center. So let's take a look now and try to think if we can come up with a model that might explain what's going on. Every feldspar that we have tested and heated, if it's an Amazonite, has lost color when we heat it, and every one that we have tested when we irradiate it gains color, returns the color, or even becomes more intense than it was to begin with. But that, first of all, raises the question, where does the radiation come from in nature? This is potassium aluminum silicate, a potassium feldspar. Typically it's microcline if it's ordered. That's the blue color. But where's the radiation coming from? Well, the answer is that it comes from the feldspar itself. Feldspar contains potassium, of course, that's one of the major components, and a very small fraction of all potassium is the isotope potassium-40, and that is naturally radioactive. It has a very long half-life, 1.2 billion years, so it's feeble radiation. But this feldspar has been sitting in the ground for possibly many tens of millions to hundreds of millions of years, building up a small, continuous, integrated exposure to this ionizing radiation. And if you sit around for 100 million years soaking up this radiation, that becomes a very sizable dose of radiation, and that might cause color changes in the feldspar. Let's take a look. After all of these studies, we finally come to a model of what we think is going on in Amazonite. We believe that the gamma radiation from the feldspar itself interacts with the water molecules which are structurally bound within the feldspar, and they rip them apart. The energy of the gamma ray is enormous compared to the binding energy of the H and the OH of the water molecules, and this can break the water molecules apart, forming what we call radical ions. Ions that have an unusual number of electrons, H radical and OH radical. And the OH radical in particular is a very strong oxidant. It can easily react with things and oxidize them to a higher oxidation state. And our model says that the OH radical interacts with the lead plus 2, which forms naturally in the feldspar, and changes it into lead plus 3. We know from chemical theory that lead plus 2 is going to have basically no color at all, but we know that lead plus 3 is going to have the ability to have very strong color because of the way it has electrons oriented in the crystal. So we believe now that the lead plus 3 is the cause of the color of the blue feldspar. It's the cause of the color of the green feldspar, but because of the ordering of the aluminum and silicon ions, they cause slightly different electrostatic environments around the lead plus 3. The color can either be blue in the ordered feldspar or it can shift to more of a greenish color in the disordered feldspar. So we feel very confident now that amazonite feldspar is a radiation color involving lead, water molecules, and natural radiation coming from the feldspar itself. Let's take a look now at another example of where radiation causes color. And now I want to home in on tourmaline. Tourmaline is certainly one of my favorite minerals. It's in the cabinets behind me, and we've spent a lot of time analyzing tourmaline over the years. Currently, the tourmaline group, I should say. Tourmaline is a group of minerals that share a common structure. It's not a single mineral. There are 36 different tourmaline species in the tourmaline group. Some of them I'm sure are well known to you: dravite, albaite, lidocodite, and schorl. These are the ones pictured in the bottom in that order from left to right. They're pretty common. Most people know about them. They're abundant tourmalines, relatively speaking. But there are also many very uncommon species of tourmaline that represent different chemical compositions. Dutroite and all the other ones on the list are examples of these. Probably most of you have never seen them. They're rare, they're uncommon. Some of them exist in minute quantities. They have different chemistries from the common tourmaline, but all of them have been studied and documented, and they've been approved by the International Mineralogical Association as new and different species of tourmalines. Today I want to concentrate on the albaite tourmaline. This is the very common one that we find in pegmatites. And albaite chemically is a sodium, lithium, aluminum, boro, hydroxy silicate. And as we said before, sodium, aluminum, and silicate do not cause color. Lithium also does not cause color. Borate does not cause color either, nor does hydroxide. So if albaite tourmaline had the textbook perfect example of the compound composition that you see there, it would be colorless. And rarely you can find them in nature that are colorless. But most commonly, albaite tourmaline grows in a pegmatite where there's iron, manganese, tourmaline, and fluorine available at the same time. Fluorine itself is not going to significantly influence the color of the tourmaline, but iron, manganese, and titanium are important chromophores, elements that can cause color in minerals like tourmaline. We're going to go to the Himalaya Mine because that's a mine I've been in and studied samples from that particular mine, addressing the origin of color. The Himalaya Mine in past times has been one of the largest producer of gems and specimen-grade tourmaline in all of North America for much of the 20th century. For some of the 20th century, it was in fact the most productive gem mine in all of North America. If you go there today, you will find that it's located in Southern California. Let's take a look at a map here before we actually enter the mine. This is a map of Southern California. And Los Angeles, LA is up in the upper left. You can see the border with Mexico, San Diego. And then I have a little dash pointing to a little reservoir called Lake Henshaw. This is important for the tourmaline pegmatite area. Let's blow this up. There's Lake Henshaw in the upper right. And the area within the yellow box is the area of the Himalaya Pegmatite. Let's magnify that and see what happens. Here it is, the Himalaya Mine. As you can see the disturbed ground. It's a pegmatite that runs from above the disturbed area, then down and around to what we call the San Diego Mine. That's all part of the same pegmatite, but it's under a different ownership and it was given a different name. If you want to go to the Himalaya Mine, you take the roads, except you're going to end up at this block gate. It's not open to the public, it's on private land, and unless you're one of the people that has the mining contract to be there, you basically are not going to get into the Himalaya Mine or the adjacent San Diego mine. I was very fortunate to have made good friendship with Bill Larson, who was mining the Himalaya Mine for many, many years, and I've had the opportunity to go there and to bring students into the mine and conduct research. So let's open the gate, so to speak, drive up and go to the Himalaya Mine. This is what was the opening of the Himalaya Mine when Bill Larson was mining it. The lady in front is Alice Keller, the former editor of the journal Gems and Gemology. Now we're going to go into the mine, we're going to walk back, and we're going to get into the actual pegmatite itself and see what that looks like. This is the Himalaya Pegmatite. The dark host rock on top and on the bottom, the lighter colored pegmatite in the center. The pegmatite's about 1 meter thick. It formed when the host rock was cooling and cracked because of contraction. Then the residual magma that was still in the magma body made its way into the crack, and that became the pegmatite. This is really sort of the last gasp of crystallization of a large body of rock that was crystallizing deep in the earth. You can see the black tourmaline coming down from the top. These are shoral dravite tourmalines. When they enter a gem pocket, they turn into albaite. You can see the beautiful pink lepidolite pods there. The miners know when you hit lepidolite, you could be close to a gem pocket. Towards the center, you can see some large feldspars. There's also quartz in there. This is the typical Himalaya pegmatite. But there's no gem pocket in this particular field of view. So what we want to do is we want to now take a look at what a gem pocket would have looked like. And this is one after it was mined. The lady, Cynthia, below gives you the scale, and the large opening above her head was a gem pocket that contained gem tourmaline and perhaps other minerals, quartz and other things. But that was been all mined out. But this is a typical size of a gem pocket. There can be significant quantities of gem tourmaline, carving quality tourmaline, specimen tourmaline in a pocket like that. And there were many such pockets like that in the Himalaya pegmatite. Here's a gigantic pocket. This goes back more than 10 feet. This pocket contained large quantities of tourmaline, gem tourmaline, carving tourmaline, specimen tourmaline, and you can see to the left of the helmet, there's some crystals of quartz that had not been removed. But imagine the quantities of tourmaline and other things that came out of a pocket of this size, big enough for multiple people to go inside, crawl up, and go to sleep. That is a gigantic pocket from the Himalaya Mine. Here's another pocket that actually still has the tourmaline in it. This is Bill Larson, who was mining it at the time. You can see numerous tourmaline crystals, sort of the darker red material, mixed in with the white matrix. The white matrix might be zeolites and carbonates, things that formed when low temperature fluids came in probably. And you can also see that some of the tourmaline seem to be cracked. There seem to be breaks in the tourmaline. And that's because these things formed maybe 8 or 10 kilometers below the surface of the Earth. And when they came to the surface, they were brought up by earthquake activity, tectonic motion, and these can be very violent events that can cause the tourmalines to break in the pockets, fall, whatever. And over many tens of millions of years of geologic time, they made their way up to the surface, where they're now accessible and being mined like you see here. Now, please remember, I am interested in the origin of color of these red tourmalines. Why do they have red color? Well, let's begin to explore that now a little bit further. Bill Larson was very kind to us. He let us come in while he was mining a gem pocket, a somewhat small pocket. You can see the mining instrument he used. It's a dull screwdriver. He uses it to poke into the pocket and bring out the various tourmalines and other things. In his hand, you can see some small tourmalines. And he was generous enough to give these to us for the research activities that we wanted to conduct at Caltech. He also let us put radiation counting equipment inside the pocket, Geiger counter equipment, basically. So we could measure the ambient flux of radiation coming from the minerals surrounding the pocket, many of which are feldspars. We did all this. We took the samples back to our lab. One of the very first things that we did is we took one of the samples and we sliced it up like a loaf of bread, and we polished the little wafers on both sides and made them transparent like a window. The window you see here is roughly 1.5 or so millimeters thick. And you can see the pink color of the tourmaline as it came out of the ground. Now, the questions we want to ask: can we do things that will give us more insight into the nature of the color of the tourmaline? And one of the things we did was the very same thing we did with the feldspar. We heated it up, but this time only to 500 degrees. That's sort of the temperature at which these things begin to form. They form at relatively low temperatures. They may form in a matter of a day, a few days or so. But the point is that we're going to heat them up for a very short period of time and see how stable the color is. And as you can see here, when we heated it, the color nearly disappeared completely, even though it was a very short amount of time at 500 degrees. Like in the case of the feldspar, this is the behavior that we expect to see from radiation-induced color. So the next thing we want to do is to take the sample we decolorized when we heated it. We want to expose it in the laboratory to ionizing radiation. And we did that. We know that the element potassium, which is the component of the feldspar surrounding the gem pocket, orthoclase and microcline in this case, is radioactive, as we said before, emitting potassium-40 gamma rays. And the important thing is that these gamma rays are so energetic, they can easily penetrate through 10 centimeters of rock and not lose all of their energy. So for the geological time that this pegmatite existed, close to 90-some million years, even though the radiation from the feldspar was feeble, over geologic time, the effect of this radiation really built up and did things to the tourmaline. So we took the sample that we heated to remove the color, and we gave it a dose in the laboratory of radiation equivalent to 92 million years of the natural radiation. We knew the natural radiation rate because we'd measured the radiation in the gem pocket with our counting equipment. And in the lab, we have facilities that can do this radiation in a controlled environment. And to our great happiness, when we gave it the 92 million years of laboratory radiation, the color came back almost exactly to the color that the tourmaline had when it came out of the pegmatite, when it came out of the ground. So I think we have shown very clearly that the color in these tourmalines is a color coming from natural radiation. We can understand that they didn't grow that way, but they became that way when they were irradiated primarily from the potassium in the gem pocket surroundings, which was largely feldspar, potassium feldspar. The other thing that we did is we gave these tourmalines much more radiation than they would have obtained in the natural geologic environment. Let's give them several 100 million years of gamma radiation and see what happens. And there you can see the answer on the screen. They turn darker. Nature in no way has taken this process to completion. Whatever is going on is only partially complete in the 92 million years of geologic time in the Himalaya Mine. But if these crystals were to stay around for hundreds of millions of more years, they would turn darker and darker from the process of natural radiation. They're a very similar thing to what we saw in the feldspars. The next thing we have to do is obtain chemical analyses on these tourmalines. And here is a very typical result that we find in a pink tourmaline from the Himalaya Mine. First of all of the pink tourmalines have manganese in them. It has to be a relatively modest amount of manganese, on the order of about 0.1% plus or minus a little bit. But even more importantly, they have to be very low in iron content, and they have to be very low in titanium content. Iron in the tourmaline would cause it to turn blue. And the blue color is a strong color. It could easily mask a lot of the pink color of the manganese. And if there's iron and tourmaline both present, They interact with each other and they cause the tourmaline to turn green. And again, this is a strong coloration. It can easily mask or modify the pink color of the tourmaline. And if there's a lot of iron and a lot of titanium, it's going to be black. It's going to be a schorl or a dravite or one of the other dark tourmalines. So the formula you see here is the formula for a typical pink tourmaline: low iron, low titanium, and some modest amount of manganese. And let's see how that plays out with the manganese. The manganese ion is in the tourmaline. It's in the structure of the tourmaline. But when the gamma ray comes through, the gamma ray from the potassium-40, it comes through with a very large amount of energy. It comes through with like 1,000, what we call 1,000 electron volts of energy. Huge amount of energy compared to the binding energy of an electron in the manganese. That's just a couple tens of electron volts. The gamma ray comes through with an enormously larger amount of energy passing through the crystal, where the electromagnetic force of the gamma ray can literally strip an electron away from the manganese and send it cascading through the crystal somewhere, oxidizing the manganese to a higher oxidation state. Now we know that happens because when we look at the optical absorption spectrum of the tourmaline, we can see it very clearly demonstrated. The big peak in the center is the peak from manganese plus 3. There's a modest amount of that in the natural pale pink tourmaline. When we heat it, we see the manganese 3 level go down, and when we irradiate the tourmaline, we see the manganese 3 level rise. Also, when we heat the crystal to remove the color, we see a very weak feature from manganese plus 2 growing, and that feature goes down when we give it large amounts of radiation. From chemical principles, we understand that manganese plus 2 is a very weak absorber of light. It does not significantly cause color. But manganese 3 is very effective at absorbing light, and it can cause the color. You see the absorption of light on the pattern I show you, where the center of the absorption is in the greenish yellow portion of the spectrum, allowing, when the curve is low, the red colors and a little bit of the blue to come through, which is that slightly purplish red color of the albaite tourmaline. So we have now shown that radiation generates the manganese plus 3, and the manganese plus 3 is the cause of the color in these tourmalines. This basically is a display of what's going on, the science behind the coloration in a nutshell. When the tourmalines grow deep in the ground at modest temperatures, 500 degrees and lower, when the pegmatites form, the manganese enters the tourmaline as manganese in the 2+ oxidation state. That has very little ability to cause color, so these tourmalines will be very pale colored, effectively almost colorless. But over geologic time, potassium-40 gamma rays from the surrounding rock and from other materials potentially in the gem pocket irradiate the tourmaline. They strip away the electron from manganese, oxidizing it from the 2+ up to the 3+ oxidation state. And that is the pink color that we see in normal albaites. And if you want, you can take that tourmaline to a laboratory and give it even more radiation than nature gave it, and that's going to make it even darker in color, like the one that you see here on the left, or on the right-hand side, and that is simply causing more manganese plus 3 to form from the manganese 2 in the sample. Again, nature does not take this to completion in the typical pegmatites. There's a lot more manganese 2 just waiting to be irradiated and oxidized if they would stay in the ground for a longer period of time. This is done commercially, as you might expect. Here's the economic reason why. This is tourmaline as it's mined on the right-hand side, an Afghani tourmaline, very pale pink color. You can't really sell it as a gemstone, it's too pale. But if you irradiate it in a laboratory, you can greatly enhance the amount of pink color, making it to a much more viable gemstone after it's faceted. Yes, this is being done commercially on some significant scale. And also you can heat the tourmalines if they're too dark, make them lighter, as well as irradiate them to make them darker, both for the specimen market and for particularly the gemstone market. This is an irradiation facility that I have seen. It's a facility where we have ingots of the element cobalt isotope number 60. Here we're looking at it when it's submerged under a large swimming pool to protect the photographer from being irradiated. And the glow that you see is the glow of the science fiction movies. That's called Cherenkov radiation. And that occurs when the gamma rays come out of the cobalt-60 at a velocity higher than they can normally travel in water and have to dump their excess energy, and that comes out as visible light. For irradiating the tourmalines, the cobalt-60 ingots would be taken out of the water and put in air, then the tourmaline would be allowed to be in contact with these ingots of cobalt-60 and be irradiated. On the right-hand side, you can see an example of one that I did, and you can see the before, basically an almost completely colorless tourmaline after a large exposure to ionizing radiation turned into the very dark red tourmaline that you see there. So yes, this is a viable commercial process. As we come towards the end here, now I'd like to show you some examples of other minerals that are naturally irradiated. We talked about the albaite tourmaline, which is a very widely available naturally irradiated mineral. But amethyst is also an example of irradiation. Amethyst involves incorporating iron +3 into the quartz. Gamma radiation will oxidize the iron from iron +3 that is pale, very pale colored in quartz, to the very vibrant purple color, which is iron in the +4 oxidation state. Next, we have a piece of ametrine, the variety of quartz that contains both amethyst and citrine. And again, the amethyst portion of this is because of natural ionizing radiation in the mine in Bolivia. Blue topaz, natural blue topaz occurs. It's not particularly common, but again, it's an example of natural ionizing radiation causing color in the topaz. On the lower left, you can see a brownish topaz. This material is very common. This is an example of ionizing radiation causing the brown color. But this is a very unstable color. It will fade in a matter of hours in bright sunlight. Blue topaz in the upper right is quite stable to fading, where the brown topaz can fade quite rapidly. Then the next we have a kunzite variety of the mineral spodumene. As this is mined in California and some of the mines in Afghanistan, it comes out with a distinctly green tint like you see there. That is an example of radiation color, but it's also manganese. But here the manganese has been oxidized from the +2 to the +3 to the +4 oxidation state, and that is the green color. But it's a very unstable color. In a matter of few hours exposure to sunlight, the green color completely goes away, and the kunzite turns into the pink color, which those of you who have kunzite are much more familiar with. The next example is an example of golden beryl. This one is from the Ukraine. That is also an example of irradiation color. Iron is oxidized when it forms in beryl from +2 to +3, and that gives rise to the yellow color. It's heat treated in a laboratory after being mined to turn it back to the +2 color, which is the beautiful blue color of the gem aquamarine and the specimen aquamarine. Then we have halite, common sodium chloride, common salt. When that is exposed to ionizing radiation, the radiation interacts with the sodium ions. It causes little colloidal particles of metallic sodium to form, and that is the blue color that you see here in the halite. Finally, we have an example of quartz, that is smoky quartz. That's also an irradiation color. In this case, it's a minor amount of aluminum in the quartz that substitutes for the silicon. It is irradiated, an electron is stripped away from the ALO4 unit, and that gives rise to the smoky color. It doesn't stop here, however. There's a little bit more we can talk about. We now know from very reliable sources that have been out for a long time that people are using laboratory methods to color topaz to make the blue gem and other minerals of commerce. Let's, as a concluding effort, take a look at one of these reliable reports on how people are using radiation to alter the color of gemstones. Okay, it's the National Enquirer. And they're quoting a professor from the California Institute of Technology by the name of Rossman, who has shown that, in fact, early on, many years ago, that radiation technology was being used to color blue topaz, which is now the important gemstone of commerce. It's a very stable color, a beautiful color, no danger with it, but it is certainly something that has been done for a long time. On that happy note, I'm going to come to the end of my talk without mentioning gems. No, I got to mention gems. I got to mention gems that are irradiated. Tourmaline as a gemstone can be irradiated. Diamonds are irradiated in a wide variety of colors. And like I said, blue topaz is an example of natural ionizing radiation and an example of laboratory radiation to make the gemstone of commerce. Quinzite can be irradiated from pink to green. I would advise you, if it's an irradiated quinzite, don't buy it unless you want to have a stone that's going to fade in a very short period of time. It's very unstable. Even if you keep it in darkness, the color will fade away. And then finally, even synthetic stones, synthetic diamond, synthetic amethyst is being irradiated to generate the colors that we find in the natural environment. Now, on that happy note, I will come to the end of my talk. I thank you for the opportunity, and I'm very happy to take questions.
All right. Thank you, George. That was fantastic, as we anticipated it would be. So I think we have a lot of questions that came up. So we want to go ahead. Jessica, do you want to go ahead and ask some of those questions?
Sure. Hi, George. Thank you. It's great you could join us.
Oh, my pleasure.
So we do have a number of questions for you. So I'm just going to take it from the top. It looks like Aaron asks, when you say that radiation damage centers are also called color centers, are all color centers or F centers related to radiation damage?
In common parlance, that's often the way that people refer to them. Sometimes people casually refer to other things like metal atoms as color centers, but I think you'll find in the scientific literature, primarily it's referring to the radiation-induced colors.
Thank you. Let's see. Robert wonders if the pale blue albite clevelandite from the Homestead Pass, Jefferson County, Montana, would fall into this category.
We've examined a number of pale blue albites from different localities around the world. Yes, all of them that are blue contain lead. It's a much more dilute version of the Amazonite color, but it is a lead-induced color.
And Ron wonders if is it the potassium 40 that colors the smoky quartz associated with the Amazonite in Colorado?
Right. Any source of radiation will contribute, but potassium is going to be the dominant source, particularly in the potassium feldspar pegmatite.
And Greg wonders how much gamma radiation from cosmic sources at high altitudes in Colorado, if exposed at the surface.
The surface exposure will be relatively brief when a piece of feldspar is exposed to the surface. So that amount of radiation is really minuscule compared to a few 100 million years sitting below the ground where cosmic radiation does not penetrate.
Angela wonders if one can tell if Amazonite is naturally irradiated or if it's been irradiated in a lab.
I don't know how to do that. Sorry.
Let's see. Rob wonders, says there are orthoclase pseudomorphs after mariolite from Afghanistan with a sky blue color. Have you looked at this material?
No, I've never had one of those to play with. If somebody wants to send me one, I'll be more than happy to look. Hint, hint, hint.
If Roberts says, is the source of the color zoning in tourmaline, for example, zonation from green to pink to blue, due to relative concentrations of other elements such as iron and titanium?
Absolutely. The blue cap on a blue cap tourmaline is iron +2, which is the dominant ion. When we get the green tourmalines, we have a mixture of iron +2 and titanium 4 that have to simultaneously be present. And if we have large concentrations of iron +2 and titanium +4 and iron +3, the whole thing turns black. The schorls, the phoitites, the dravites.
You're so on the ball. This is great. Iron 3 versus iron 4 in amethyst. From Eric. I was unaware of the +4 state. Where else do we see this oxidation state?
Almost never. It's an incredibly rare oxidation state. It has very little stability in a chem lab environment, but trapped inside a mineral like quartz, it can persist for geologic time.
See, that's more of a statement than a question here. Let's see. Rob says, the blue halite is colloidal sodium. Is that blue from Rayleigh scattering that makes the sky blue?
No, sodium itself, intrinsically, when it's colloidal, will absorb the particular wavelengths of light to make it blue. So it's not scattering. Scattering can be a factor in many things, but it's actually an intrinsic color of the sodium in the case of the halite.
And Greg wonders, Greg says, sapphire can be heated to a darker blue. Can it be irradiated too?
Sapphire can certainly be irradiated. We can throw it in an irradiator. But typically when I irradiate the corundum materials, you gain an orangish color to them, or a kind of a yellowy brown color. And in my experience, these are largely quite unstable colors. If I take a colorless sapphire and irradiate it, which I've done many times, I get a kind of a beautiful golden, slightly brownish yellow color that comes out. But in a matter of a week, the color has faded away.
Wow. Which is a good question. Let's see. Ray asks, he is told that schorl is not black, but actually a deep, deep blue, and that if thin enough, its blue color can be seen. Is that true?
Absolutely. If you make a thin section, 10, 20, 30 micrometers thick, most schorls will be blue or a blue-brown or even a dark greenish-brown color. I don't think I've ever thinned a schorl down to a few micrometers thick that has not been transparent with some other innuendo of color.
Oh, wow. Do irradiated tourmalines fade upon exposure to UV and sunlight like some other irradiated gems?
In my personal experience, it may span something like 20, 30 years of stones being out in intermittent room light. I have not observed what I would call any significant fading whatsoever of the color. Bill Larson, who, of course, mined the Himalaya Mine for many years, has been to China, where he has seen tourmalines that were mined in the early portions of the 1900s. And it is his opinion that after a century of exposure to sunlight, there is noticeable fading in the pink tourmalines.
Oh, very cool. Oh, Erin says that she can send a chunk.
Thank you, Erin. I'll take it.
Hold her to that. We have another question from Rob. Is the blue in sodalite from colloidal sodium or some sulfur complex?
No, sodalite is a sulfur complex. The blue color is typically a little chain of 1, 2, 3 sulfur atoms in a row with a negative charge.
And can you address the blue caused by sun on barite?
I have been working on that, but I do not have an answer yet to give you atomistically.
Well, we'll look forward to that in a future presentation, I guess. Mm-hmm. See, have I missed any questions? These are all the questions I see.
Yeah, Linda Smith was asking, would rose quartz be an result of irradiation?
No, rose quartz, in the classical sense, massive veins of quartz that have rose color, is due to tiny, thin, hair-like inclusions of an aluminoborosilicate that has the pink color. It's a mineral related to dumortierite, color coming from iron and titanium. However, there is a variety of quartz that forms crystals that have a pinkish color. I call them pink quartz, not rose quartz. For example, from Galicia, Brazil, or Argentina. And those are radiation colors coming from aluminum and phosphorus substitution in the quartz. But the vast majority of common everyday bulk, big hunks of rose quartz, that's inclusions of pink material, not radiation.
Fascinating. Yeah. I have a question, George. This is Julian. The photograph that's behind you on the wall, is that a Rossmanite?
Yeah, it's 3 different species of tourmaline. This one comes from Elba, Italy. The bottom part, the sort of crinkly, partly turbid part, That's the phase albaite, the common tourmaline species. The very top of the crystal, which is black, is the tourmaline species phoitite. And the beautiful, clear, transparent area I'm now pointing to is the Rossmanite.
Very good. Yeah. Well, tourmaline is my favorite mineral too, and specimen number 1 in my collection was a shoral that I collected a few hundred yards from my house when I was a kid. So that's what got me started. So
it got me started too in science when I got a sample of tourmaline when I was back in grade school, and I became fascinated by the color of the material. And ever since, I pursued a career literally looking at the color of minerals, including tourmaline.
We are all very grateful that of several things that you did pursue that career, that you've been very successful and that you're sharing your time, but you also have a talent for making incredibly difficult concepts very understandable. And that's one of the other reasons that we wanted you as a speaker today. So thank you very much.
Oh, my pleasure indeed. Happy to do this.
Can I ask a quick question before we move on? There is an occurrence supposedly of Rossmanite at the Tanko mine in Manitoba. Are you aware of that? And can you confirm if indeed that is Rossmanite?
I can confirm it is probably the largest crystals of Rossmanite in the world, at least discovered so far. The first crystal of Rossmanite from the Tanko Pegmatite was obtained by a group from the University of Winnipeg, Manitoba. They went into the mine, they sampled tourmaline, they brought a little teeny piece of a tourmaline crystal 2/3 of a meter long. A few months later, they got around to analyzing it, and oh my gosh, it turned out to be Rossmanite. But when they went back to the mine, that crystal was all mined out. But there are many other smaller pink tourmalines in the Tanko Pegmatite that have been shown occasionally to be Rossmanite. The trouble is, to really determine it absolutely, it's an expensive analysis to do involving detailed electron microprobe analyses. It's not something you can easily do by simple, quick methods.
May I ask one quick further question? Uh-oh.
Sorry, I'm just sharing a picture of a Rossmanite from Tanko there.
Whoever had another question, go ahead.
The other question was, with these very submicroscopic inclusions in the rose quartz, calling the rose color, do they organize to the point that they are the source for the asterism?
Yes, sometimes they'll go along the A-axis of the quartz, giving rise to the beautiful asterism.
Thank you.
Thank you so much, George.